Thank you for giving me the opportunity to speak to you all. I thought I would make to the youth campus, but I couldn't. However, I can give my talk nevertheless. The talk starts at its origins in categorical closure operators, and then in the categorical neighborhood operators as in Holgate and Schlapal's paper, and then it gave Inani's master's thesis with Razafindra Katur. And while going through this master's thesis, I realized that much of this has been known under the name of neighborhood operators, as well as special cases of categorical closure operators in several places. And moreover, in all of these cases, the generalization was done keeping in mind some topological examples. The only example where which was possibly a little bit different was by Herlich, Bentley and Lowen in this paper, Improving Constructions in Topology, where they studied it under the name of pre-topological and pseudo-topological spaces. Trying to understand this construction gave the material of this talk. Let's look into topological spaces. A topological space is alternatively given by a function on a set X to the set of filters and satisfies these two properties 1 and 2. So the first property is very simple. It says that if you, let's think of these filters xi x as, if we start to think of them as neighborhoods of X, so if U is a neighborhood of X, then U should contain X. That's a very natural condition. And the second condition is, if U is a neighborhood of X, then there exists another neighborhood such that for every point in that neighborhood, U is also a neighborhood of that. It seems to, and then once we have a filter satisfying for each point these two conditions, one can get a unique topology, and topology is actually generated by such. So there is a one correspondence between topologies on X and function space. But this second condition is the more intriguing one, which one needs to look into. And the earliest thing that comes to our mind is a sequence of sequences. So suppose in each row we have sequences which converge as shown to P1, P2, P3 and so on. And I also suppose that the convergence, that is P1, P2, that sequence also converges to P. Then it is quite natural to expect that the double sequence converges. And if somehow, remember, given a sequence, one can create a filter using the tail sequences. And then this condition that I have phrased in this diagram can be phrased in terms of those filters. And this filter version is exactly this second condition. So it is quite natural. And it is at the heart of the idea of being a neighborhood. If we do a little more of algebra, we see that this is equivalent to this set theoretic or algebraic condition. And a filter containing the neighborhood filter in topology, we say that it converges to X. So we start to think that whether the condition of convergence of filters is actually a lattice theoretic condition or not. So we have now completely had it in terms of filters. Once we start to think this way, then we see that filters on a space is nothing else but filters in a certain lattice, that is the lattice of subsets. So the main focus is on a lattice of subsets or sub-objects, as we say in categories. But then the question turns out that all lattices are not atomic. So we have to remove our focus from atomic lattices. Filters can be defined, in fact, on any semi-lattice. To define a filter which is an upset, so define an upset means you require an order, and it should be closed under finite sections. So any semi-lattice suffices. However, to have good properties of filters, it is known that a lattice is distributed if and only if the filters is coherent frame. And a coherent frame is nothing else but a compact algebraic lattice whose binary meet of compact elements is compact. Then how do we come up with these subsets? Well, it is very natural to look into the subsets of a set via functions as coming from the monic part. So there is a factorization system present in the category. So we start off in our setup considering a finitely category with finite coproducts. The finite coproducts part will be required in the next one. So I just recall what is a proper factorization. A factorization system is given by a pair of morphisms. E is a set of epimorphisms, M is a set of monomorphisms, and for every morphism there is a factorization of that in terms of an M morphism and an E morphism. Just like as our sets, we can take E to be surjections and M to be projections. And this factorization has to be unique, otherwise we cannot do anything with it. So that's this diagonal, existence of this diagonal is the other way of saying it. Categorically, we often say that the E morphisms is orthogonal to the M morphisms, some kind of strongness is there. If, now whether do we have two thus categories? So any finitely complete and finitely co-complete category with all intersections has an epi and extremal monofactorization. So we are not actually in the air. So every well-powered, that means if you have a set of sub-objects which is finitely complete and finitely co-complete, we will have this. Now we need a proper factorization system. If we have a proper factorization system, the finite coproducts part tell us a little more. It tells us that the E class is not very small, it at least contains the extremal epimorphisms. I'm sorry, it at least contains the extremal epimorphisms and is contained inside the epimorphisms. So it gives us a bound of E. So that is where we want our E not to be very, very trivial, and that is why we need this finite coproducts part. Obviously now sub-objects are not all the subsets, but admissible ones. So admissibility comes from the selected monomorphisms, M, and sub-objects are actually the recollection. Again, this is how we order monomorphisms. which is a subset kind of a thing. And in the presence of finite completeness, subobjects is always a semi-lattice, but we assume further that it's a distributive lattice and complete lattice. Now about examples. Yes, any questions, please? About examples, every Grothendieck topos is an example of such. If you have a small co-complete and extensive category, for instance, locales is an example of such. That is there. If you have a category like this and you take a bundle, you have an example of such. So there are several examples that we find in this case of our context. So our context is, it has finitely complete, proper factorization, and the subobjects make a distributive complete lattice. Now we define the neighborhoods. Neighborhood definition comes in 3 phases. The first, so we have removed the notion of atomicity. The moment we remove the notion of atomicity, we are going to say neighborhoods, we can think of it as a neighborhood of a subset. Obviously, if you have a neighborhood, anything larger than that should also be a neighborhood. Intersection of neighborhoods must be a neighborhood. So the collection of neighborhood itself is a. And if you have a neighborhood of a subset A, and B is a bigger subset, the neighborhoods of B must also be neighborhoods of A. So it becomes an order-preserving map, but with the reverse order. It's an order-reversing map from subobjects, or in other words, an order-preserving map from subobjects of, as written. So the first part is that neighborhoods must contain that set. So n is a neighborhood of M if M is smaller than or equal to N. So that's called just a pre-neighborhood. That's the first stage. Pre-neighborhoods can be then ordered pointwise, and once we ordered them pointwise, we see that it is a complete lattice with the obvious order of join of filters and meet of intersection of filters. So that is that just comes through from the lattice of filters. This is the next one is the weak neighborhood. This is something to do about that crucial condition about neighborhood, which was the second point which I mentioned. And let's see what does this mean. This strange thing means some kind of an interpolability. So if you have n to be a neighborhood of H, you can interpolate another neighborhood of M such that n is also a neighborhood of M. And then obviously the interpolation goes on. So the weak neighborhoods are precisely interpolative pre-neighborhoods. And then the class of neighborhoods again make a complete lattice, but not a sub one, not a complete sublattice. The join is exactly the same as in pre-neighborhoods, but in weak neighborhood, we have the largest weak neighborhood contained inside any pre-neighborhood. So that's how we get hold of the meet. So it's also a complete lattice. Finally comes the neighborhood. Now over here, remember we have forgotten that our lattices are atomic. So we are actually speaking of something like neighborhoods of sets. And if we have to reconcile the singletons, if we think of singletons, so every set is a join of singletons. So how do we get hold of it? The most natural thing would be that a neighborhood of a set intersection of all the neighborhoods of each of the points. And that is exactly the neighborhood. What is the neighborhood? Neighborhood on X is such that it preserves this meets. So thus we come to the neighborhood. It comes in 3 stages. The neighborhoods of X is also a complete lattice, and that is where most of this work is about to show that we can give several descriptions of neighborhoods, and many things come up. Even in this scarce content of assumptions, we can prove many familiar facts about topological spaces and neighborhoods. So first, let's see what's that. Given any neighborhood, say given any pre-neighborhood, I define it's a set of opens, O mu, by equation 4. Those are precisely those which are themselves their own neighborhood. And the interior with respect to mu of m would be the join of those mu opens which are inside. It turns out that this interior operation is an interior operation. It is interior of M is intensive. It is order preserving and idempotent. And mu open subobjects, so mu open sets are actually its fixed points. But the mu open sets are only closed under finite means. And mu open closed they are closed under arbitrary joins if and only if every interior is mu open. So that's the first thing that comes up. It's closed under arbitrary joins if and only if every interior is also open. And if you have that every interior is mu open, then there is an alternative way of describing your mu-m as being generated by these. The mu unfiltered is generated by opens, or as precisely those inside whose interior M is contained. Now, in that case, if every mu interior is open, then the interior operator becomes a Kuratowski operator. And neighborhoods are particular such. So, if we have a neighborhood instead of neighborhood, then every mu interior is mu open. Have our usual description of our interior that P is a neighborhood of M if and only if M is contained in the interior of P and it is a Kuratowski. So now comes the first part. Suppose we take the collection of pre-neighborhoods whose interiors are open. It is a sublattice of pre-neighborhoods, and Px be the Kuratowski interior operations that we can define on this lattice. Obviously, we can point by order A, make it a poset. And interior, as we have just now observed, becomes order preserved map, but in fact, it is a split epimorphism. And it's so it has an inverse, and its right inverse is also its left adjoint. And moreover, this interior is actually fixing. So P composed, the right in it is fixed on neighborhoods. That means it says that if you look into this interior in its fibers, you have the smallest element to be the neighborhood. and neighborhoods correspond to Kuratowski operators. So that's another way of specifying neighborhood filters by specifying Kuratowski interiors or Kuratowski operators. As we know from our usual exercises in topology, but this is happening, remember, in any finitely complete category with products and so on. So we are in a much more general case than sets. Okay. Now about the mu open sets. The mu open sets are, we saw, if and only if every mu interior is open, then the mu open sets are closed under arbitrary joins. We know that our topological spaces, we define the topology is closed under arbitrary joins and finite means. So that's what we took as a definition of a pseudo-frame set. Well, not very happy with the name, but okay. Now the set of pseudo-frame sets can be denoted as, it is obviously a complete lattice by intuition. And neighborhoods are actually given by these frame sets. So that is the next observation. So starting from a pseudo-frame set, you know exactly what the neighborhood that I am creating, and that provides a very good isomorphism between these complete lattices of neighborhoods and pseudo-frame sets. And this is natural linears. So this gives us a way to compute the meets and joins in neighborhoods. So we first look into the opens and then go back by this correspondence. So that gives us the conversion between several. Okay. So now, let me topology. Remember, topology had another feature which only was not that visible in sets, because sets are completely distributive lattices. So a neighborhood is an internal topology if the lattice of opens is a frame, that means the finite meets distribute over arbitrary joins. And then this is the so-called kernel topology. Now we need to look into continuous maps. So the EM factorization already gives us a jump. I have written that there exists F with image adjunction, and the other one is by two factor. Just quick look. Suppose we have n. This is the subset. We pull it back. That's the inverse image. And if we have a subset here, we take the EM factorization of this, and that gives us the image. Now, since this is a order, we have the forward filter and the backward filter. The forward filter is the filter generated by the images, and the backward filter is the filter by the pre-image. Okay. So pre-neighborhood morphisms. Given any pre-neighborhood mu on x and phi on y, so the most natural thing is if P is a neighborhood of n, the codomain, then F inverse P must be a neighborhood of F inverse n in the domain. It's the most natural kind of property that we face in topological spaces, and hence it's transported here. Suppose if we have this, in fact, we know that these are the several equivalent conditions, and a very short diagrammatic way of it is this. So what is happening? Suppose we have this map from X to Y, so that is inducing for us the junctions on the top row as well as the junctions on the bottom row between the filters. Now, our pre-neighborhoods were just order-preserving vertical maps as shown mu and phi. So what is happening is f is going to be continuous if and only if you do all kinds of composites. The right-hand side thing is less than the left-hand side composite. So mu composed F inverse will be greater than inverse filter composed psi. That is one of the conditions. This is the last conditions. So you see all these conditions can be phrased like this. On composition, the right-hand side one will be smaller than the left-hand side one. So that's the whole picture. All right. Now, pre-A is the category of internal pre-neighborhood spaces, where X is an object, mu is a pre-neighborhood on X, and the morphisms are pre-neighborhood morphisms. W neighborhood is the full neighborhood category of full subcategory of internal weak neighborhoods. Now, NBD is not the full subcategory. Take the internal neighborhood spaces, but the morphisms are restricted to those whose F inverse preserve arbitrary joins. The inverse image preserving arbitrary joins is something which we do not question in the case of sets. But that may not be true. For instance, even in locales, the inverse image doesn't preserve arbitrary joins. So it is something which has to be taken. And the fact that inverse image preserves arbitrary joins have very nice equivalence. So it produces further advantages on the level of filters, and it preserves on the inverse image filter. So we had this one automatically from our context. If we assume that F inverse preserves arbitrary joins, then we further have right inverse for all F, universal quantifier on the top, and another one, a further left adjoint on the level of filters. And the formulas are like this, which is very simple to obtain. And top A again is the full subcategory of internal topological spaces. Once we have this, well, that is another category which came up very formally. So we only take those morphisms, we restrict the morphisms of A to those where inverse image preserves joins. So these are all the categories that I spoke of, and this is the initial picture. So the first set of results that we get is this. Topological. The word topological means that we can now, it enables us to speak about weak things, weak topologies, strong topologies, so quotient things, weak products, weak topologies, and so on. So that means if I have a collection of weak neighborhood spaces, so if I have a collection of weak neighborhood spaces, xi, mu, I can speak of its product. or in other words, or I can, given a collection of weak neighborhood spaces and maps, I can bring out a map on the codomain, on the domain, the smallest one, which makes each one of these maps contiguous. So that is the idea of creating a weak neighborhood. So we can do that for each one of these cases: neighborhoods, weak neighborhoods over A. But for neighborhood, we can do it only for certain morphisms, provided the morphism serves arbitrary joins. And neighborhoods are, weak neighborhoods are reflective in cycles. Now, this is the first digression that we have in the case of sets, which essentially tells us that studying topology in other contexts is not that fruitful as studying neighborhoods. Neighborhoods is the real picture of internal topologies in other contexts than sets. So what is the result? Says that if for every object there exists large internal topology, if and only if the topologies make a full reflective subcategory of the neighborhoods, and topologies is topological over APPJ. So if we have to have a notion of a internal topology which is faithful to our belief, at least it should be topological over APPJ, well, then there must be a largest internal topology. And in fact, if we look into the case of locales, where internal topologies have been studied very recently by Dubé and Igedo, very fruitfully, successfully, to describe some extensions. They were studying internal topologies on locales actually, but they were not looking into them as topological spaces. They were looking into them as free objects, so free neighborhoods. Now, the next thing is, if every F preserved join, then APPJ is A, and neighborhoods become reflective beside this, and it is a strange mixture of many things that come over here, shows that this condition, if F inverse preserved joins, this is equivalent to saying that that the sub-objects make right. So in that, so that's the result which we have. So sub-object lattices are frames, then topologies become neighborhoods, F inverse preserved joins, and and this is exactly the situation which we see in the case of sets, but we don't see this even in the case of locales. So in the case of locales, this part doesn't appear. In the case of topological spaces, it appears, and it turns out that the internal topological spaces, or top of top, becomes the bitopological spaces. So now, having studied this case, limits, we know from Yoneda, studying of limits is makes it easier. So let's look into co-limits, that means quotients. The regular epimorphisms of Preneighbourhoods have a very similar picture as quotient topological spaces, and it is precisely given by this, provided F is a regular epimorphism of Preneighbourhoods, if and only if It's a regular epimorphism of A, and U is a neighborhood of Y, if and only if F inverse U is a neighborhood of F inverse Y. And another thing is U must contain Y. The first condition not present in the case of sets, and the reason being some Frobenius condition or Chevalier condition. We are going to come there, and that also forces every regular epimorphism of topological spaces to be. But it is not the case over here. We need some more conditions. Regarding the hereditary part of regular epimorphisms, let's look. Here is possibly a complete picture. I'll come back. Yeah. So there are 1, 2, 3, 4, 5, 6. The sixth one being the regular epimorphisms are hereditary. E is fullback stable. Let's see in sets, yes, our epimorphisms are fullback stable, and that's why we have this condition. But there are several other conditions, and these conditions which you see, for instance, the third one, so the top one on the right hand side, there exists F inverse T. That is exactly called the Frobenius condition. And what I'm saying is, I'm trying to find more and more stricter Frobenius conditions instead of for all A or for all E and so on. And these conditions are known also as some kind of Chevalier conditions for monomorphisms. So this it's a very, very restrictive set of conditions for E, for the factorization system, which leads to the hereditary nature of the regular epimorphisms. And that is what has been completely pictured here. Regular epimorphisms of neighborhood spaces have also been looked into. They are pretty similar. Their connections with pseudo-open maps have also been established. They're also pretty similar, so but I want to say something else. What is the way forward? Where are we moving? So we started off with a category. And given any morphism, we have these subobject lattices, and there was this adjunction. This same morphism F induced an adjunction over these filters, and there was a straight connection between these filters, and then we described everything in terms of the symbols that we have seen on this slide. Nothing else was required. Sorry, two more things. The came out suddenly was the connection between the second and the third layer. So one was the up filter, and the other one was filters coming back to the meet. And it turned out that the meet is the left adjoint to the up. And on a closer look, it seems that this and a few more commutativity conditions between these maps were all that was required in the proofs. So this reminds us of the following. Remember, we have two very, very wide examples of categories. One is a monoid with one object, and poset that post one morphism. So Somehow we have a category with multiplication. In fact, Benabu called it categories of Weck multiplication. We have the notion of a monad. There are two special cases, the Cartesian and the co-Cartesian ones. The linear ones are which are somehow where both of them are true. Now on the posital side, which is obviously I'm referring to, so the left-hand side is completely looks into the algebraic aspect. The right-hand side some kind of analysis. We have been looking in topological spaces, field theory. We look into subtopics. In other places like science or in schemes, we look into quotients. But somewhere where all of this kind of seems to meet is vector spaces which have both a spatial picture as well as a algebraic computational picture and so on. But something is missing. What should be in the place of? Zurab suggested some kind of form. And, well, what this present work suggests is something like this, because these subs are actually the fibers of some special functor from some B to A. This was the codomain part of the factorization. So this is where possibly, I don't know, or this is leading to. And obviously the second step that I still need to look into is the category of pseudo topological spaces, which I still believe would be done using all the symbols here on this slide, and possibly some more relations, which would possibly enable me to understand what is this Zurab's form completely, and possibly sometime I'll be able to describe the topic. Thanks.